Welcome back to the deep dive. I want to start today with a scenario that I think every single developer has nightmares about.
Oh, I think I know where this is going.
It's 4 p.m. on a Friday. You've spent 3 months building the perfect backend for a client. The architecture is pristine. The code compiles without a single warning. You are ready to launch, and then you get the email.
Let me guess. We've decided to change the database vendor.
Yeah.
Or maybe, actually, we need this web app to also work offline as a desktop application.
Exactly. And just like that, your beautiful, pristine architecture, it just turns into a pile of rubble. Today, we aren't just talking about writing code. We are talking about the universal truth of our industry. Things change.
They always change. If you bet against change, you lose.
Yeah.
Every single time. And honestly, if your code can't handle change, it's not actually good code, no matter how clean the syntax looks.
That is a bold statement. So the mission for this deep dive is figuring out how to stop building these, houses of cards and start building systems that can actually survive the real world. We're pulling from Chapter 2 of the Bible of Software Development, The Pragmatic Programmer, specifically the section titled A Pragmatic Approach.
And to ground that theory in reality, we're going to overlap it with the Class 7 slides on software architecture. We'll look at how we evolved from the messy mainframes of the 90s to the service-oriented architectures we use today.
And there's also some notes on aspect-oriented programming and the usual housekeeping for the course.
Yeah.
So let's start with the big picture philosophy. The notes describe the essence of good design. Now, usually when people talk about design, they use words like clean or elegant or maybe performant. But the authors here argue that good design actually boils down to just 3 letters, ETC.
Easier to change. It sounds incredibly simplistic, almost like a throwaway line in a fortune cookie.
It really does.
But if you actually treat it as a razor or ruthless decision-making tool, it completely changes how you work.
So how do you actually apply that? Because easier to change feels so subjective. What's easy for me might be hard for you.
It sounds subjective, but it's really not. Imagine you're staring at your IDE. You have a choice. Do I hard code this file path, or do I put it in a config file?
Okay.
Do I tightly bind this function to an Oracle database, or do I put an interface in front of it? You just ask, if the file moves, or if we switch to Postgres, which path makes my life miserable and which one makes it a 5-minute fix?
It's essentially a litmus test for future pain.
Precisely. And the authors argue that almost every other design principle we worship, decoupling, encapsulation, separation of concerns, there aren't separate rules. They're just special cases of ETC.
So we decouple things so that they are easier to change.
Exactly. We encapsulate data so that the implementation is easier to change. ETC is the parent of them all.
One of the most famous children of that parent principle is DRY, don't repeat yourself. But I feel like this is the most misunderstood acronym in coding history.
It is genuinely painful to watch sometimes. If you grab a junior developer and ask them what DRY means, they'll say, don't copy and paste lines of code.
Which is, generally good advice, right?
Right. It is, but it misses the entire point. You can have code that looks completely different, but still violates the DRY principle. The notes make a crucial distinction. DRY is about the duplication of knowledge or intent, not just text.
Okay, give me a concrete example of that. How do I duplicate knowledge without copying code?
Well, think about a validation rule. Let's say usernames must be at least 8 characters long.
Okay.
You enforce that in your database schema with a specific length constraint, that's SQL. Then you want the UI to be responsive, so you write a JavaScript function on the front end that checks the length so the user gets a red box immediately.
Makes sense.
Then you have a Java backend service that checks it again before saving, just to be safe.
Okay, I see where this is going. 3 different languages. SQL, JavaScript, Java. No copy pasting happened. The text is totally different.
Correct. But you have triplicated the knowledge of that business rule. The 8 characters, it lives in 3 places. If the business decides actually 8 characters is too long, let's make it 6, you have to remember to update it in 3 separate places.
And if you forget one, your system is inconsistent. You violated DRY.
Exactly.
That seems almost unavoidable, though. You need validation in the browser for UX, and you need it in the database for data integrity. You can't just skip one.
You don't skip them, but you automate the synchronization. The source notes suggest using generators. You make one of those the master source of truth, say the database schema,
Nice.
And then you use a script to generate the validation code for the other layers.
So the intent is defined once.
That's the key.
The notes also mention a variation of this called interdeveloper duplication. This one hit a bit close to home for me.
Oh, the classic, we didn't talk to each other problem.
Right. You're building the billing module, I'm building the shipping module. We both need to validate a phone number. I write a regex function, you write a totally different regex function.
And now the system has a split personality. Depending on which page the user is on, the phone number rules change. One accepts dashes, one doesn't. It's not a code problem, it's a communication problem.
So what's the fix? The notes suggest a librarian.
Yeah, it sounds a bit old school, I know. But the concept is solid. You need a central repository or a clear leader who says, hey, before you write a utility class, check common utils. If it's not there, write it, put it there, and tell everyone. It's about active leadership.
This idea of keeping things clean and separate brings us to the geometry lesson of the day, orthogonality.
I love this term. It makes you sound very smart in meetings, but it's actually really intuitive.
Conceptually, it's just two lines meeting at a right angle, right?
But visually, yes. If you have a graph with an x-axis and a y-axis, moving a point along the x-axis doesn't change its y position. They're independent. In software, it means that changes in one part of the system shouldn't ripple out and break unrelated parts.
Right, the helicopter analogy. If the controls are orthogonal, moving the stick forward makes you go forward. If they aren't, moving the stick forward makes you go forward and spin to the left and drop altitude.
Exactly. And you do not want to fly that helicopter. But we build software like that all the time. You change the font size on an invoice, and suddenly the database calculation for tax breaks, that is non-orthogonal. It's coupled.
The class slides give us a really stark history lesson on this. There's a slide labeled 1990s architecture that looks like a bowl of spaghetti just exploded.
That slide triggers PTSD for anyone who worked in the 90s. You see mainframes running COBOL, Power Builder apps for the UI, maybe some VB scripts. But the key isn't the technology, it's the lines connecting them.
They are everywhere. It looks like a spider web.
Everything is talking to everything. The Power Builder app is reaching directly into the mainframe's database tables. The batch jobs are reading files that the UI writes. It is a mess of coupling.
So if you wanted to change anything,
You had to check everything. If you updated the mainframe, the Power Builder app crashed.
and that's the definition of a fragile system. You touch it, it breaks.
Right. So the slides transition us to Tier 1 service-based architecture and then Tier 2 SOA, or service-oriented architecture. This isn't just a trend. This is the industry trying to impose orthogonality on that chaos.
It looks much more organized on the slide. You have these horizontal layers, consumers at the top, business services, common services, and then infrastructure at the bottom.
And look closely at the arrows. They only go down. And they only go to the next layer. The consumers say, a web app, it talks to the business service. It does not talk to the database. It doesn't even know the database exists.
And this is enforced at the hardware level too, according to the physical architecture slide.
Yes, this is crucial for modern deployment. The slide shows separate Linux boxes. You have a machine running Tomcat for the web layer, a separate machine for the queue manager, a whole separate box for the database. This is orthogonality in metal.
So you can upgrade the Linux kernel on the web server without risking the database server.
Exactly. They are physically decoupled. We move from these monolithic blocks where everything touches everything to cooperating modules that speak through very strict interfaces.
But here's the catch. We're sitting here talking about designing these perfect decoupled systems, but in the real world, and definitely in this course, you often have to start building before you fully understand what you're building.
Oh, uncertainty is the default state. You never know less about a project than the day you start it.
The notes present two specific tools for dealing with this: tracer bullets and prototypes. Now, I've heard people use these terms interchangeably. Oh, just whip up a prototype, just fire a tracer.
And the pragmatic programmer authors get very annoyed if you mix them up. They are completely different tools for different problems. It's like using a screwdriver to hammer a nail. It's going to go badly.
Okay, so let's start with tracer bullets.
And the analogy comes from the military. It's nighttime. You can't see the target. You don't sit there and do a heavy physics calculation. You load a round that glows, you fire it, and you see where it goes. Then you adjust your aim.
In code, what is that glowing round?
It's a thin slice of real code. Let's say you're building that order system we talked about.
Yeah.
A tracer bullet would be. The user clicks buy, the signal goes to the controller calls a dummy service, the service puts a dummy row in the database, and the database says, okay, back to the UI.
So it doesn't actually process the payment or check inventory?
No, it does nothing useful. But, and this is the big difference, it is production quality code. It compiles, It connects all the architectural layers. It proves the plumbing works. You keep that tracer bullet code. You flesh it out later. It's the skeleton of your final system.
Okay, so a tracer bullet is a skeleton that you keep. Now, contrast that with a prototype.
A prototype is a disposable experiment. You build a prototype to answer one specific question. Is this UI intuitive?
Yeah.
Or can this algorithm sort a million records in under a second?
And once you have the answer,
you delete the code. You throw it away.
That's the hard part, isn't it? The notes warn about a specific trap here.
It's the management trap. You build a UI prototype to show the client how the workflow could look. You stick it together with duct tape and hard-coded strings. It looks great. The client loves it. Your boss says, great, it's basically done. Ship it next week.
And you're sitting there knowing the back end is just a text file and a prayer?
Exactly. If you don't clarify that this is a disposable toy, you will be forced to turn it into production code. And that is how you end up with that spaghetti architecture. So, rule is tracers for structure, prototypes for risk. And always throw the prototype away.
Okay, moving on to something a bit more advanced. The notes and slides have a section on advanced decoupling using something called AOP aspect-oriented programming. This sounds like the black diamond run of software architecture.
It is where we try to solve the problem of code. That can't be orthogonal.
What do you mean? I thought everything could be orthogonal.
Well, think about logging or security or transaction management. These things don't belong to one specific module. You need them everywhere. You need to log every database access. You need to check security on every administrative action.
Right. These are the cross-cutting concerns.
Exactly. Now, without AOP, what do? You violate DRY. You copy-paste logger.info entering method at the top of 500 different functions. It just clutters your business logic. You can't see the algorithm for all the logging noise.
So how does aspect-oriented programming fix this?
It uses a concept called weaving. The slides mention tools like AspectJ. Basically, you write your logging code in one separate file and aspect. Then you define cut points. You say, apply this logging aspect to any method that starts with the word get or set.
And the compiler just does the rest.
Yes. A pre-compiler takes your clean business code and your separate logging aspect, and it weaves them together into the final executable. The running code has the logging, but your source code stays clean.
It sounds almost like magic.
It feels like magic, and that's actually the downside listed in the notes. It can be magical in a bad way. If you're debugging, the code you're stepping through isn't exactly the code you wrote in your editor.
So things are happening, logs are writing, security exceptions are being thrown that you can't see in the file in front of you.
Precisely. It creates what the notes call shy code that doesn't reveal too much, but maybe it's too shy for debugging sometimes.
So use it for clear-cut things like logging or transactions, but maybe not core business logic.
I think that's the safe bet, yeah.
We're coming into the home stretch here. I want to talk about the mindset of the professional pragmatist. There's a section on how you operate as an engineer, specifically regarding reversibility.
This circles right back to ETC. The pragmatic programmer assumes they are wrong. Or at least they assume that the decision they make today might be wrong tomorrow.
There are no final decisions. I like that.
Right. We often get paralyzed trying to pick the perfect database or the perfect framework because we think it's a marriage. But if you design with reversibility in mind, if you decouple properly, it's not a marriage, it's a date. If the database doesn't work out, you can swap it.
That takes the pressure off. But let's talk about pressure. Estimating. The notes have a fantastic observation about how the units of time you use affect people's expectations.
Oh, this is pure psychology. If I tell you a project will take 6 months, what do you hear?
I hear sometime around half a year, maybe 5 months, maybe 7. It's vague.
Exactly. But what if I tell you it'll take 180 days?
I assume you have a spreadsheet. I assume you've calculated it down to the hour.
Right. So the lesson is don't mislead with precision. If you are guessing, use a vague unit, say about 2 quarters.
Yeah.
If you're sure, say 3 days. Match your unit to your uncertainty.
And the notes have a golden rule for when you're put on the spot. You're in the hallway, the VP walks up and asks how long to build that feature.
You must fight the urge to guess. The only correct answer is, I'll get back to you.
Never guess in the hallway.
Never. Because that guess becomes a commitment in their mind instantly. Go to your desk, break it down, check your tracer bullets, then give a number.
Before we wrap up, we should probably touch on the team dynamics mentioned in the wiki page's outline slide. This is specifically for the class context, but it applies to any dev shop.
Yes. Software is a team sport. The slide highlights that you need defined processes, core values, standards, downloads, training. But Those things don't just happen by magic. They need owners.
The syllabus calls them discussion leaders.
Exactly. If you are a leader, you can't just write code. You have to update the wiki. You have to document the decisions. If the team decides we're using Postgres, write it down. Otherwise, 2 weeks later, someone installs MySQL and you have inter-developer duplication all over again.
Documentation reduces the need for constant communication. It's the DRY principle applied to people.
Precisely. If it's not on the wiki, it didn't happen.
All right, let's bring this deep dive in for a landing. If you're about to open your IDE and start Lab 2, what are the 3 big takeaways to keep in your head?
Number 1, code for change. Every time you write a line, ask yourself, if I have to change this in 6 months, will I hate myself? If the answer is yes, refactor it now.
Number 2,
decouple relentlessly. Look at those Tier 1 and Tier 2 architecture slides. Build lasagna, not spaghetti. Keep your UI away from your database. Use services.
and the third one?
Know your tools. Don't confuse a prototype with a tracer bullet. If you need to prove the plumbing works, fire a tracer and keep the code. If you need to see if the user likes the button color, build a prototype and throw it away.
Throw it away before your manager sees it.
Or at least before they promise it to a customer.
A quick bit of housekeeping for the class. You have an immediate deadline. Lab 2 is due this Thursday, February 5th. Do not miss that.
And for the discussion leaders, check the slides. You need to update the reading discussion notes page on the wiki. Record your overview, your decisions, and any open items. Your team is relying on that single source of truth.
And if life has completely fallen apart this week, the syllabus does mention those 3-day extension coupons. Check the fine print. They are for individual assignments only, not team stuff.
Use them wisely. You don't get an infinite supply.
We want to leave you with one final thought on that concept of reversibility.
We spend so much time fearing mistakes. What if I choose the wrong language? What if I choose the wrong library? But if you are truly pragmatic, if you build systems that are orthogonal and easy to change, you never have to fear being wrong.
Because you can always fix it.
You can always reverse it. And that freedom is what makes this job fun.
That's it for this deep dive. Go forth and decouple.
See you next time.